Okay, so near the end of the previous lecture, I forgot to share a screen. So basically, like the last 8 minutes or so of the video was just a blank screen. I'm gonna haven't edited the video, but I'm gonna just chop that last segment off. So it might just cut off might just cut off abruptly. So I just want to say that that's why it did. So what I'm going to do is I'm going to start out with basically just recalling what we did in the last lecture and then just going over the part that I didn't get to show you. So let me share my screen. Make sure I do that this time. All right, let's see. So hopefully you can see what I'm seeing. Oops. I don't have OneNote open. Oops. All right, um, so basically last time I was trying to motivate why we care about calculus. Like what's the problem that motivated the introduction of calculus? What were the problems that these mathematicians and these physicists were trying to solve? And they were very concrete, uh, real world problems, trying to describe instantaneous motion. How do you describe that? We know how to make sense of average, or instantaneous velocity. We know how to talk about average speed or average velocity. That's a pretty straightforward concept. But isn't clear how to make sense of instantaneous. And what we did was we found out that um, this instantaneous velocity should be some sort of limit. So basically, what we did was we did a lot actually. Let's see, I'm not sure exactly where to start. Yeah, so we imagine that we're in a particle moving in one dimension, and the position can be described say, by some function p right here. There's my pen. There we go. It can be described by some function p right here. So it's just function from 0 to infinity to r. And you can think about the domain as the time, a given instant of time. And then the codomain is just a position on the real line. And given a t, p of t denotes the position relative to t. So basically we have this real line and you start here and then you just kind of travel forward and then you travel backwards some spot and then you can plot it right here. Um, all right, so let's see. Please don't. And so the question is, how do we, so yeah, the plot of this will look like something like this. It passes through the origin, then it goes in the negative direction, right here. So this is like represents it's moving away from the origin, then this part represents the fact that it's moving back towards it, and then this means it moves. Well, this point right here means it moved right through the origin, and then this segment of the graph means it moved past the origin in the negative direction. And so the question is, this motivating question is how to describe the velocity, the instantaneous velocity of this particle, this instantaneous speed or instantaneous rate of change. And so we have basically, so we have a point in time and t0. We want to describe the velocity. So we have t0 is right here, and then maybe you're at this position along the real line, and you can consider points nearby, and you can compute an average velocity over this interval from t1 to t2. So it's just going to be the average velocity is just the change in position and divided by the change in time. So where did you start? Where did you end? That'll give you this distance that you traveled. And then right here is just how the change in time is just how long did it take you to travel between those two points in space. Um, and then we have this, we're deliberately choosing T1 and T2 to contain this point right here. So this average velocity right here is going to give us a rough estimate of the instantaneous velocity at that time. And we're gonna call the velocity instantaneous velocity. So let's say v is going to be a function from 0 to infinity to r. And the idea is that if we take this interval right here, containing this point to be smaller, and we compute another average, we're going to get a better estimate of the instantaneous velocity. So the idea is to just keep repeating this process over and over, just take smaller and smaller and smaller intervals. Um, and then so in other words, we're going to take a limit, sort of limit of these intervals containing t0 and getting smaller. And so every time you shrink this interval, you're going to compute the average velocity. And so you take start with an interval containing t0, compute the average velocity. Take a smaller interval containing t0, compute the average velocity. And you're going to get this sequence of numbers, these average velocities that should approach the instantaneous velocity. Now, so the best way to do this though is not to think about t0, t1, and t2, but just to have this parameter that you introduce, h, which can be positive, negative, but it's going to be small. It's going to be a very small number. Actually, the absolute value is specifically going to be small. So when you look at t0 plus h, depending on whether it's positive or negative, it could be on the left or the right, but it's going to be close. It's going to be very close. It could even be maybe right here or right here. It could be very close to this point right here. And so this is like when h varies over all very small numbers, this is like a whole collection of points in time that are very close to t0. So what we want to do is we want to take a sort of, this is going to be by definition, if you're in computer science, this notation right here, when you have some colon equal sign, just means definition. It's defined to be. So you have these symbols right here that don't mean anything, and you use this. Now you're giving meaning to the symbols. That's what this notation means. You see this in computer science a lot. Um, so this is going to be this is going to be our instantaneous velocity at t0, and we want to define what it should be. Well, it should be a sort of limit of these average velocities. So we're taking a limit as h goes to 0 of this whole quotient right here. This whole quotient. And oops. I think I'm gonna have to open a new document because I think there's too much in it. Um, and of course we're being really vague here, intentionally vague here as to what a limit is, but we have this rough idea. It's like this, you have this parameter h, and you just keep computing these average velocities. This will give you like a sequence of numbers. In the same way, you have pi has a sequence of rational numbers approximated. You can have this sequence of these quotients approximating the true instantaneous velocity. So it's the same sort of thing. And like this sequence of numbers, they tend to some number. They approach, they converge to some number. This is going to be all this language we're using is going to be made very precise in this lecture, actually, because we're gonna talk about limits now, eventually, I should say, and then we're gonna talk about them from an intuitive standpoint, but then we're gonna actually state a rigorous definition. So this is roughly what the instantaneous velocity is going to be. And the next thing I wanted to talk about is that got cut off is to note there's another feature of this. And this is like this other problem I mentioned in the first lecture about the tangent line problem. So this whole discussion is related to this tangent line problem. So basically a tangent line to a curve, so you have a curve like we do here, is a line that touches the curve and it follows the same direction as the curve at the point of contact. So we have this point right here. This is our t0. Well, you can see it. This point right here. And we have the red line, oops, is this tangent line. And then if you look at points that are close to t0, like of the form t0 plus h, and you look at this, you can look at the line passing through this point right here and this point right here. And then what happens is as t goes to 0, this point right here slides along to this point here. And these are called secant lines. So these secant lines are approaching the tangent line. So I have this GIF right here. I want to show you to illustrate this problem, this idea of a tangent line. So hopefully you can see this. So basically we have this curve, and then at I guess 0.5 we have this is like our time 1.5 or whatever, half a second, half a minute, whatever, it doesn't matter. You have this tangent line, this is the green line, if it touches the curve at one spot and it goes like in the same direction as the curve. If you're imagining you're going from left to right, I guess. Well, actually, it doesn't matter. Um, and you can take points either to the left or the right. So you have the gift starts out with points to the left. And you can like this point is sliding. You can think it's like a bead and it's sliding towards the green point. And so all the purple line is are secant lines, and they are approaching this tangent line. So um what this what this thing that we're computing right here is actually ends up being the slope. So when we take this limit, this quotient right here ends up being the slope of the line through this point and this point. And if you, it's a pretty simple calculation. See what is the slope of a line through the point? Well, you take the difference in the y coordinate. So this is the y coordinate, and this is the other y coordinate. So that's the numerator. And then you take a difference in the x coordinates. This is the x coordinate, and this is the x coordinate. And if you do this calculation right here, it's really simple. You can see that this is exactly this right here is exactly the thing we're computing up here, which you can't see right now, but you will hopefully in a minute. Um, let's see, right here. This instantaneous velocity, this quotient right here is exactly the um this this quotient is exactly the slope of the line passing through those 2 points. And then you're taking a limit. So you're taking these the slopes of these secant lines, and the limit gives you the slope of the tangent line. Like it's like that point, that bead sliding along the curve. You keep basically sliding it until it basically coincides with the green dot right here, and that will give you the slope of the tangent line. That's another problem that was kind of that mathematicians were interested in, and it ends up being directly related to this idea of instantaneous rate of change. All right, so I'm gonna open, as I said, I'm gonna open up another because I think, all right, let's add another page. I haven't really been consistent with these lectures page numbers. I should have, so I can keep everything separate. Anyways, I don't know what lecture we're on. Doesn't matter. So now the I want to make a point now. So we've been talking about velocity, instantaneous velocity, but it turns out you can really talk about instantaneous rate of change of anything. We don't have to just talk about velocity. That was just the one example we looked at and tried to like develop some ideas of calculus. But it turns out you can talk about, say, um, oh, I don't know, you could say, like, suppose you have like this is like a silly toy model that you think about in physics. Like you have a rod, it's like a metal rod, and then maybe there, I don't know, I can't really draw, so there's like a heat source down here, whatever. Heat source. Heat source, and say it's at the middle of the rod, and like you can imagine that you just flick on this heat source and it's going to heat up the rod, and there's going to be like a distribution. It's going to be really hot near the middle, and then it's going to like taper out. And you can talk about how quickly does this metal rod heat up, and you can talk about the instantaneous rate at which it heats up. So you can talk about this limit. You can do the same sort of limit that you did for uh, average rate of change. Or you imagine like maybe like you have a charged particle, and you give an initial like push with some electromagnetic field, so you impart kinetic energy to it. And so it's like, and then you maybe have a particle right here, a charged particle, and you give it some initial push with electromagnetic field, so it has some initial energy, but then you have like a field pushing this way. Um, Actually, no, I don't want to say that because that would not be a realistic situation. What I was going to say is not. It's been a while since I thought about physics, so it's hard to come up with examples. But really, physics contains all the motivation you need. So I have like it's like being propelled initially in this way, but then I have a, let's say I don't want the electromagnetic field to be orthogonal. So I have this electromagnetic field pushing in the other direction, and as it's going along, it's like because this is pushing in the other direction, um, it's reducing its electromagnet or it's reducing its kinetic energy. And so you can talk about maybe say the kinetic energy as a function of time. Like as it passes through this electromagnetic field, it's going to start slowing down and probably end up being pushed in the other direction at some point. But you can talk about like what is its kinetic energy? How does it depend upon time? And then you can talk about instantaneous rate of change of kinetic energy with respect to time. So, oh, I did not mean to click that. See, share my screen. So you can imagine that this is a calculus is going to be a very powerful tool, and there's a lot of different phenomenon you can describe. So there's just really kind of basic examples in physics you might encounter. I don't know if I have the details completely accurate, but hopefully you get the rough idea though. Um, so we want to talk about in this next section we want to talk about limits more generally. So we can just take limits of really any function, but it's not necessarily the case that the limit will exist, but we can certainly take this limit and we can determine whether it exists or not. So this is 2.2, limits of a function. Actually, I might not even use this OneNote document. There's a lot of pictures in this. So I might actually just pull up the book, but let me just write this down anyway. So limit of a function. And so the idea is we want to move away from just thinking specifically about limits of that quotient, about limits of, say, average rate of changes to give us velocity, but we'll just talk about limits of anything really, any kind of function. And so we're going to start abstracting, where this is the process of mathematics. You have a really concrete problem you're working on, and then you want to like abstract the basic essential details of that example and then state things more formally and mathematically. So that's what we're going to do now. So let me just pull the book up. This I actually think it's helpful or helpful. So for example, we're going to look at yeah, so we saw how limits arise when we want to find the tangent to a curve or the velocity of an object. But now we want to try to abstract this everything that we've done, like get the essential ideas out and then formalize everything. So let's look at this function. We want to look at values of x near 1. So we're going to basically take a limit as we approach 1. Now, there's two different directions I can approach 1, right? I can approach 1 from the left. Let me get my marker up. I can approach 1 from the left, or I can approach 1 from the right. And if you do some calculations, if you plug in 0.5 into this function right here, you get this number 0.6. If you plug in 0.9, you get 0.52. If you plug in 0.99, you get 0.50. 0.999, you get 0.500. So it looks like this thing, at least on the left-hand side. So remember, what is the limit? It's like you basically like look at points when you're taking the limit towards a point, you look at points near it and you evaluate your function at it. In the case of the velocity, we were evaluating our function was that quotient. We were evaluating our quotient at points closer and closer and closer to a given point. In this case, we're not really, I mean, this is a quotient, but it's not like it's not, this doesn't necessarily represent, this function right here doesn't necessarily represent a rate of change, an average rate of change of something. So the idea is like we take points closer and closer to 1, we get this sequence right here, and then we can plug them into here, get this sequence, and as this indicates, this is just going to keep going down. You have this infinite list, and this list right here is our not or this column I should say right here are numbers getting closer and closer to 1. And you can see that from the right, from the left, and you can see that when these numbers right here are getting closer and closer to 0.5. And the same story is, we have the same story for x on the right of 1. You take numbers that are getting closer and closer to one from the right. So you take 0.5, 1.5, 1.1, 1.01, 1.001, etc. These are numbers, this column right here are numbers approaching one from the left. And again, you're seeing that this number, the function, the output, when you plug these numbers in, these numbers are getting closer and closer to 0.5. So whatever a limit is, because we haven't really made this precise, whatever a limit is, we want to, it should be that. So let me say that actually, whatever a limit is. So let me say whatever this symbol means, it should be the case that when you take the limit as x goes to one, either from the left or right, of our function, I'll just write it out, was x minus one over x squared minus one, it should be 1/2, 0.5. Well, however you define a limit, we want it to be such that when you do this computation right here, you get 0.5, 1/2. So this will be a guide for us. This is going to be a guide for this example right here, and many other examples are going to be a guide for us as to how to make this idea of a limit precise. So, okay, they just wrote that there. So we have this is the graph here. You can see there's a hole at one because you can't plug -1 in. But even though you can't plug -1 in, and so 0.5, or sorry, you can't plug one in, you can't get 0.5 as an output, but the graph still approaches it, even though it's not defined at this point. So that's another kind of key idea from this example is that even if the function is not defined at that point, you can still take a limit at that point. So here's the intuitive definition of a limit. So we have a function f of x is defined, um, it's going to be defined when x is near, say, a number a. So in our the example above, a was equal to 1. So you have some, what that means to be defined near some number a is you're defined on some open interval that contains a, but maybe a is not a element in that open interval itself. So for example, like in the above one, you could do, well, actually, that's not entirely accurate. You don't want it to be, it won't be an open interval, but it'd be what's called an open set. You can't really get an escape topology. So we're gonna see like there's some really topological ideas. There's these open intervals, but to have an open you can't have an open interval. Um you can't have an open interval this, or sorry. So it says that f is defined as some open interval containing a, except possibly a itself. Oh, I see what it's saying. I'm sorry, I misread it. So yeah, you have a full interval. I was gonna say like you could chop it up like this with a union. No, say two. Um, but they're saying that the interval can contain a, yes, and f will be defined on the whole interval except possibly at a itself. And so this notation right here means that well, first of all, how do you say it? You say it's the limit of f of x as x approaches a equals L. And basically what that means is if you take values um that you can make f of x as close as you wish, arbitrarily close to L, by looking at x that are very close to A, and that's either on the left or the right of A, but not it doesn't necessarily have to be equal to A, like in the example above. And so being sufficiently close to A means like you have some open set containing A, and you're looking at points in that open set. You're taking x from that open interval. So what does that mean? So this equation right here, these symbols just means that the f of x approaches L as x approaches A. So that is to say that f of x tends to get closer and closer to this number A as x gets closer and closer to sorry, f of x gets closer and closer to L as x gets closer and closer to A. So here are just some examples, I guess. Yeah, I don't know if these are really that helpful. Computing these, we're not going to compute limits like this at all, but this just gives you a rough idea of what's going on, I guess. So this is like computing these limits numerically, but we're going to see where there's going to be an example later on where this is actually a problem. You could actually come to the wrong conclusion about what a limit equals. Um, so yeah, like these kind of examples are not really representative of what we're actually going to do. But you can see, like, you can just plug in different numbers of t. So this is represents plus or minus 1 plus or minus 0.5. And when you plug those in, you can see that it's basically approaching when you plug in these values right here, and these are of course these values are approaching 0, which is what the limit we're taking. We're taking t as it approaches 0. When you plug those numbers into the function, they're approaching what looks like to be 0.16666 repeated. And so the should limit should be, morally speaking, should be the limit. But this is by no means a proof. We have to we because we still haven't stated what does it mean to take a limit. And when you in mathematics, you always prove things by definition. So we need to state the definition, and then we can actually prove these things. So let's see what else. All right, anyways, so I'm just gonna skip this. Is this the example I want? No. I'm gonna skip. Okay, so this one we can go over, I guess. This one's gonna come up again. We'll actually be able to justify this right here. We'll actually be able to prove this rigorously. So here's the graph of this. So it's always good to have a graph in mind to like get estimates to maybe make a guess, and then you can prove your guess. And you can see, so we want to take this limit of this function right here as x goes to 0. So we have to take x values approaching from 0 from the right, and then x values approaching from the left. And if you look at the corresponding y values, the outputs, the number, when you plug it into this function right here, you can see they appear to be approaching 1, which is why the authors wrote this equation right here. This seems to be a reasonable guess. And you can also see that from the table. If you plug in all these numbers, you can see, so these numbers right here are approaching 0, and then you can see that these numbers appear to be approaching 1. I'm gonna skip this one. So now you notice a part of a limit involves this idea that you can approach a number, and since we're talking about, well, yeah, and so there are two different directions you can approach the number, approach it from the left or the right. And so this actually allows us to distinguish two types of limits. These are going to be left and right hand limits. And the reason why we want to care about them is because depending upon if I give you a random function, depending upon which direction you approach when you take the limit, you could get different answers. And so the simplest example of that is the so-called Heaviside function right here. So when t is negative, you just always evaluate to 0, and when t is non-negative, you always evaluate to 1. So here's a plot right here, and you can clearly see what if I approach 0 from the right, and I plug those numbers into the function, they're actually all constantly 1. So you would think, okay, if you were just basing your guess on the limit on that calculation alone, you might say, oh, you might say that this limit right here, as t goes to 0, of h of t is 1. That might be like a guess of yours. But now if you look at if you take points on the that are negative, the approach from the 0 from the left, and if plug it into the function, they are always 0. So then if you just based on if you try to guess based on that by looking at if you try to guess the value of this limit based on this computation from the left hand side, you might guess that the limit of h of t is 0. And there's immediately a problem. They can't both be the case. And it's going to turn out that it's neither. the limit is neither. Um, the limit, this limit does not exist. The limit of as t goes to zero of h of t does not exist. So this example means that we need to sort of distinguish between um, these two types of the left and right hand limits. So we use this notation right here. So as I said, there's no single number that h of t approaches as t approaches zero. So this right here does not exist because depending on whether you approach to the left or to the right, you're going to get different values. But what we notice is that as t approaches zero from the right, ht approaches one. So we have this equation right here. And if it approaches from the left, uh, if t approaches zero from the left, h of t approaches zero. So you have this equation. And so we have this notation right here where we have like this plus, this minus, and this plus right here to indicate which direction we are taking the limit on. So these are called one-sided limits. So this notation right here means or indicates that we're only taking values of t less than zero. So we're looking so t values of t less than zero. So we're looking at numbers to the left of zero. So this right here is the left hand limit. When you take when you take this limit as t approaches zero, negative, meaning t approaches from the left. And this is going to be the right hand limit right here. And so we can set up, so here again, this is all still in just an intuitive discussion. We're going to make everything precise though. So this is the notation in general we use for a left-hand limit. So left-hand limit. And it basically means the same thing as a normal limit. It's this, the idea is that as x approaches a, um, from the left, this limit equals L. Or it's the same thing as saying like we can make f of x arbitrarily close to L by restricting to x sufficiently close to a, but less than a, or to the, in other words, to the left of a. And then you can basically read this in the same way, but just change left to right. So basically this means the same thing. All right, and then here's going to be a fact, and it's not hard to prove actually. Once we actually state the definition of a limit, and it sort of hopefully it makes sense to you. It makes sense. What this states is that this limit right here. I'm going to pause because the dogs are barking. Hold on. Okay, sorry about that. So let me share my screen. All right, so as I was saying, so we, based on this example of this Heaviside function right here, we need to distinguish between left and right hand limits, because it might be the case that a limit does not exist at all, as in the case of this Heaviside function, based upon looking at these left and right hand limits. But we do have this nice fact right here, and that is this limit, the overall limit, the limit independent of which direction you approach, this limit right here exists and equals L. So that should really be a part of the statement. Exists and it equals L if and only if the left hand limit, so this is left hand limit, and the right hand limit exists. And they both equal L. They have to equal the same number. So you can, this gives you a way of determining whether or not a limit exists by just looking at left and right hand limits. On the other hand, it gives you a way of determining whether a limit exists by looking, let me say that again. This gives you a way of determining whether a limit does not exist based on looking at the left and right hand limits. But since this is an equivalence, you can also look at left and right hand limits. If you know they both exist and they both equal the same number L, then you know that the quote unquote overall limit exists and it has to equal that common value. So here's an example. We can look at this. So we want to use the graph to compute these limits. Again, like this is not the best way to compute limits, and you don't want to ever rely on specific numerical calculations or rely on pictures because they can be faulty, but we're just trying to get a feel for these limits. So let's just work with the picture to compute these limits first. So we have 2 as our limiting value, and then also 5, but we're going to just look at 2 first. So we have that 2, so when we approach 2 from the left, and then look at the corresponding value of the function, which is all the way up here, we can see it looks like it approaches 3. Notice it's not defined at 2. That doesn't matter. We just need to get a function doesn't need to be defined at a given number to take a limit. It just needs to be defined near it. And the function is defined near 2. And it looks like it approaches 3. On the other hand, if you approach 2 from the right, in this as in this limit, and you look at the values, it appears that it's approaching 1. So you can say that this one does not exist. Although the left and the right hand limits exist, they don't have to equal, they're not equal. So you can say that the overall limit does not exist. All right, so now in this case, G is defined at 5. And in fact, it takes this value, I guess, at 1. I can't tell. It kind of looks like it's at 1. But anyways, it doesn't matter. It's defined there. So when you take the limit as you go from the left, it looks like it's approaching 2. And we get the same thing on the right-hand side. If you take numbers approaching 5 from the right and plug them into the function, it looks like it's approaching 2. So the overall limit should be 2. And notice that's not equal to the so the overall, so because these two limits, the left hand, the right hand limit exist, and they equal the same number, you can conclude that the overall limit exists and it equals that common value of 2, which is different from what it actually equals. So note G of 5, I'm just kind of going out the graph. I guess it looks like 1. So these are not, so G of 5 does not. Let's actually write it the other way. Let's say, so G, the limit as x approaches 5 of G of x does not equal G of 5. They're not the same. And this is going to be a really key property. This relates to continuity of a function. We're going to see that this is basically the idea of continuity. So in this case, it's not, G is not continuous at 5 because we don't have equality here. And the same thing is true for we're definitely not continuous at 2. In fact, the function's not even defined at 2. It's going to turn out that in order to be continuous at a number, you have to be defined at that number. Now, G is defined at 5, but because we don't have equality of this right here, that the limit of G of x as x approaches 5 equals G of 5, it's going to be discontinuous. So this is going to like capture the idea of what it means to be continuous. And that's something you might be familiar with. You might have heard you might have heard discontinuity described as follows, that a function is continuous if when you draw the graph, you can just draw it continuously without picking up the pen. And that is an intuitive characterization of continuity, but it's going to be made more precise, more rigorous in terms of limits. All right, so here's why we should not rely on numerical calculations to compute limits. So we want to investigate this limit right here. So what we're going to do is we're going to take, so first of all, notice that the function is not defined as 0. But let's evaluate the function at smaller values of x, that is values of x close to 0. So we have 1, when you plug in 1, you get sine of 0 is 0. When you plug in 1/3, you get sine of 3 pi, which is 0. Sine of 0.1, it would be sine of 10 pi, which is also 0. So we're just getting 0. So you might guess, all right, well, it looks like your guess might be that when you take this limit of sine of pi over x, it's going to be 0. However, we're looking at very specific numbers. We're testing this limit with very specific numbers because, and the reason, um, and the numbers we're testing are of the form 1/n, right? So this will, okay, they actually didn't write that out. That's kind of annoying. 0.1 is 1/10, and 0.01 is equal to 1/100. So all the numbers that we evaluated at are of the form 1/n. But if you plug in 1/n, you get sine of n pi, and that's always 0 for any integer n. However, if you choose different values, um, you can see that the function can be equal to 1 for infinitely many values. So say like if you plug in 2/5 or 2/100, 100 ones, or just 2/100, let's just put it that way. um, all these numbers approach 0, but they all, when you plug them into the function, you get 1. So you got to be careful when you're trying to guess a limit using numerical calculations. And here's the problem. If you look at the graph, near the 0, it's oscillating between 1 and -1, like really fast. So this is kind of the reason why it says, as it says here, it oscillates between 1 and -1 infinitely often as x approaches 0. So if you take, let me just think about this for a second. If you take, let's see, you gotta be careful here. I'm trying to see. Anyway, I was trying to do a calculation like this to show that you can have f of x is equal to 1 for infinitely many numbers. Let me just try something. So 1/2n. What do you get if you plug that in? You get sine of, oh, that doesn't work. Oh, that, yeah, of course it does. If you plug in, this is a good problem actually. Something of that form. Oh, but these don't approach 0. Okay, anyways, these don't approach, this approaches 1. All right, this calculation right here will make sense later on. All right, we'll just have to take it for granted. Yeah, I can't think of a collection of numbers or sequence of numbers which approaches 0 such that they all evaluate to 1, like right here. But you can see like there's 2/5. Why? Let's actually just do 2/5. You get sine of I over 2/5, and then you get oh, 5 times pi over 2. Yeah, that should just be like maybe that's -1, I guess. Wait, no, that's a 1. That should just be 1. And the same thing with the 2/100. But it turns out there's infinitely many values of x which approach 0, but are such that f of x equals 1, like right here. And and that's also seen in this oscillatory behavior of the graph. So it's just, there's no number which approaches, it just keeps going back and forth between 1 and -1. All right, so yeah, just be careful. Turns out that this limit actually doesn't exist. Kind of for the reasons I was indicating at. All right, what about this limit right here? What happens here? This is gonna be a different type of limit, it's going to actually be motivation for the introduction of infinite limits. So if you plug in numbers, so we want to take the limit as x goes to 0 of 1 over x squared. If you take numbers that are approaching 0, so these are numbers that are approaching 0, you can see like if you take 1 over it, the idea is if you take 1 over a very small number, these numbers are getting very small. If you take 1 over a small number, you're going to get numbers that are getting bigger and bigger. So these are numbers that are getting very big. So these are going off to infinity. So, um, and this is a perfectly legitimate limit. So we want to just make this convention here that so we're going to set this definition. We want to define what it means to for a limit to be infinite. So we have a function f, and it's defined on both sides of a, except possibly a itself, just as in the limits above. It's kind of the same terminology or language that we're using to describe limits. Then this limit right here means that when you take intuitively, I should say, we're just talking intuitively here, that the values of x can be made arbitrarily large as you like, so getting closer and closer to infinity by taking x sufficiently close to a, but possibly not equal to a. And this, in most cases, with these infinite limits, your function is definitely not going to be defined as at a. All right, and then you can do the negative case right here. It's the same thing. So what does it mean to go to negative infinity? And it turns out that these, I'm just going to skip this because this is, well, let's see, these pictures helpful. I don't know, I guess they're sort of helpful. There's the blue graphs are functions, and you can see that when you approach a from, well, I should say you can also do, oh, I see what they're doing here. Right here, you can define one-sided infinite limits, and that's what you're seeing in some of these examples right here. So you can approach a from the left, and you could either get negative or positive infinity or negative infinity, or you approach a from the right, and you could get either positive or negative infinity. And so here's some graphs sort of illustrating that this is approaching from the left, and you get positive infinity. This is approaching again from this is approaching from the right, you get positive infinity. Approaching from the left, you get negative infinity. Approaching from the right, you get negative infinity. And these are actually what are called vertical asymptotes. So you might have heard about of asymptotes before. You actually need limits to make these ideas more precise. So you have a line x equals a is called a vertical asymptote. So like just in this case, we hit this red line, these red lines right here are vertical lines at a. So this vertical line x equals a is called a vertical asymptote to this curve y is equal to f of x if at least one of the following statements hold. Just one of them. They don't all, maybe they all hold. Well, actually, they can't all hold because you can't go to negative infinity, positive infinity, negative infinity. Um, but it's possible that you could have multiple of these statements could hold as true. Some of them are obviously mutually exclusive. Actually, they're kind of paired together. Like this row is mutually exclusive to this row. Like you can't have this first statement hold and this first statement hold. You can't have the second statement hold and the second statement hold simultaneously because you're talking about you're saying that the limit as you approach a from uh the left is infinity and negative infinity. That can't be both of those can't be the case. Obviously, that's contradictory. All right, so I think that's really well. There's some asymptotes calculations here. They're nothing terribly rigorous. So I'm not going to go through this one right here, this first one, but example A is a familiar one that we should all know. So we know that that the tangent function is undefined at say negative pi over 2, pi over 2, 3 pi over 2. -3 pi over 2. And it turns out that these are actually asymptotes. Um, and the reason why is, for example, let's just focus on pi over 2 and think about how tangent is defined. Recall that tangent is one way of defining tangent is that it's sine x over cosine x. And so what happens to the numerator and the denominator when you let x approach pi over 2? So when you actually equal to pi over 2, you cosine is 0. So that's bad. That's why it's undefined there. Now, when you look at the graph, well, if you when it's close when x is close to pi over 2, cosine of x will be close to 0. So it's gonna be a really small number. And sine, so let's say when x close to pi over 2, cosine x is close to 0, and sine x is close to 1. In fact, actually, sine of pi over 2, it just is 1, but it's getting close. So what we have is that as x approaches pi over 2, sine of x is approaching 1, but cosine x is approaching 0. So it's like when you take this limit, it's going to be 1 divided by a really small number, and it's getting only smaller and smaller. But if you divide 1 by a really small number, you get a really large number. And that's why the tangent goes off to positive infinity when x approaches pi over 2. So it's going off to positive infinity. And you can do the same sort of analysis for the other ones, the other asymptotes, to figure out exactly how it's approaching the asymptote. Is it going off solely for pi over 2? We know that when you approach from the left, you go to positive infinity. And that's because cosine of x, when you're to the left, when you're a bit smaller than pi over 2, cosine of x is going to be positive, and sine of x is also going to be positive. Now, when you look at x values approaching pi over 2 from the right, we know that so yeah, right here, this is what they write here. When x approaches pi over 2 from the right, cosine of x is approaching 0 from the right, left, meaning cosine is negative. But the sine x is positive and it's close to 1. So it's going to go off to negative infinity because the numerator, sine of x, is going to be positive, but the denominator, cosine of x, is going to be a small negative number and getting only smaller and smaller and smaller as you get closer and closer to pi over 2. Oh, sorry, not this one, but pi over 2 from the right. This one right here. So it's positive number, and then basically positive 1 in the numerator, small negative number getting only smaller and smaller as x approaches pi over 2 from the right. So that's why the function goes down like this as you approach pi over 2 from the right. So in summary, you have these two limits right here. And then, as I said, you can do the same sort of analysis at all the other limits. Or actually, you could probably just say because it's periodic. Yeah, you should be able to just say that because it's periodic, that you get the same behavior throughout the rest of the graph. Like, so you can extend it. So that's a one example of asymptote. They're going to show up a lot. Here's another example. You have this line y ln of x, and it has an asymptote at 0. When you approach x from the right, you get negative infinity. Okay. All right. So that's that. So now let's move on. And so I'm going to kind of combine 2.2 and 2.4. We're gonna go back to 2.3, but I want to just jump ahead to 2.4, which is on the precise limit uh precise definition of a limit. So I'm gonna just not even go through all this. I'm just gonna just pull up the definition, and then we're gonna try to make sense of it. Why is this? I'm gonna present a limit definition of the limit, and then we're gonna try to think about why is this the right definition? Why does this accurately capture all the intuitive ideas we've developed already? So here's how it works. So this is actually going to be one of the most important concepts you learn in all of mathematics. This limit of definition of a limit. It's going to come up in lots of different ways throughout mathematics, and it's also like the first time you introduced to something probably this mathematically rigorous. But there's a lot contained in this definition, and there's a lot of ways of generalizing it as well. We're not going to, of course, look at any of the generalizations, but there's a lot packed into this definition. So let's read this. So we have f is a function defined on some open interval that contains a number a, except possibly at a. So maybe it's not defined there. Um, then we have this notation here, and basically we say this is read as the limit of f of x as x approaches a is L. And this limit, we've been writing these symbols down a lot without really saying what it means. But here is where it means. This is what it means. This star right here. This is what it means. So this equation holds true if and only if for every positive small number, epsilon. So epsilon is going to be like considered as a small distance. You can find another positive number, and this is going to be even another small distance. So these numbers are going to represent distances, another small distance, such that I give you there's like a, it's like this is called sometimes an epsilon delta game. I give you an epsilon. You got to search for a number delta such that the following condition holds. If the distance from x to a is smaller than delta, so that's why x delta is said to be a small distance. So if the distance from x to a is less than delta, then the distance from f of x to L is epsilon. So in other words, like you can, if I give you an epsilon, you can a small distance that you want, and you want f of x to be that close to the limit value L, you can find a number delta to ensure that. And namely, if you look at all the x's that are this distance from delta, then this condition will hold. So that's what these symbols mean right here. It means that if whenever I give you an epsilon, that's some small distance, representing some small distance, you can find a number delta representing another small distance that will ensure that f of, f of x is epsilon close to L whenever x is delta close to A. So here's just so yeah, as I said, this x minus A is the distance from x to A. F of x, or sorry, absolute value of x minus A is the distance from x to A. Absolute value of x f of x minus L is the distance from f of x to L. And the idea is like if I give you an epsilon and you found that delta such that this whole statement or sentence or proposition is true, you could actually make epsilon even smaller. You can just make it as small as you want. You can always find a delta. The delta might be different. So for example, I could give you epsilon as 1, and then you find a delta. And then I say, all right, well now I'm going to give you epsilon equals 1/2. You got to find a delta. Delta might be different from the first choice, but that's fine. It just whenever I give you an epsilon, you can find some delta. This is not saying that there exists some delta that works for every epsilon that and makes this statement right here true. It just means that whenever I give you an epsilon, you can find a delta, possibly different every time. Who knows? Maybe not. there's no restriction that there's no such restriction being made in that way. So yeah, epsilon is going to be made arbitrarily small as you like. You can just keep taking it to be smaller and smaller and smaller. Then you can find deltas, and basically this is going to be an interval. This right here, this inequality represents an interval about x, about a. And notice there's this strict inequality right here because remember, we don't want x to equal a. Because for example, the function f might not even be defined at a. So we have to put this restriction in right here that that this is strict inequality. This absolute value is strictly greater than 0, meaning x cannot be equal to a. Or at least you don't require that x is equal to a. The function might be defined in A. Maybe it's not, but we're not making that requirement. That's not, and that's sort of this. We saw that we didn't need to make that requirement when we were talking about limits intuitively. So in words, the limit means that the distance from f of x and L can be made as small as you wish, arbitrarily small, by requiring that the distance from x to a be sufficiently small, but not 0, because you don't want x equal to a. So if you want, you can make this distance as small as you want. That is, you can pick any epsilon that you want, and but the trade-off is that you got to make sure that the distance from x to a is sufficiently small. That is, you have to be able to find this delta right here to make it work. And then, yeah, who cares about this? I mean, it's basically the same thing. But here's another reformulation. And this is a more what we would say a topological reformulation because we're not in here, we're talking about distances, right? Absolute values. But there are some spaces mathematical spaces which don't have a notion of distance. You can't measure distances between points, but you can talk about things that are like open intervals. They're going to just be called open sets. So this reformulation right here is really important, and it is like the seeds of generality. It's going to allow you to generalize mathematics. Like it is such a powerful. This reformulation right here is such a powerful reformulation. But wow, so what does this reformulation say? Well, before we can say that, let's look at this paragraph, um, because it's going to allow us to reformulate it in this way. So we have this statement right here. This absolute value is equivalent to this statement right here, right? This is just unpacking the definition of absolute value. And then what you can do is you can add a to both sides to get this inequality right here. So now you went from x minus a to being between negative delta and delta to x being between a minus delta and a plus delta. So now similarly, this inequality right here, the other inequality can be unpacked in this way right here. So what this says is that for this statement, this limit right here, means that for every epsilon, no matter how small it is, you can choose it to be as small as you wish. You can find a delta such that if x lies in this open interval, and when you go to topology, you'll just say open set, because maybe it doesn't look like an interval, it'll be some weird looking set in maybe some infinite dimensional space, who knows? And x is not equal to a, then f of x is going to lie in this open interval or open set if you're thinking more generally in topology. Lots of spaces do have distances, I should say. They have a notion of distance. It's going to be much different than the usual distance of real line. So this isn't like too much of a restriction or the talking about distance, but there are some spaces where you can't measure. There's no way of measuring. There's no distance function, in other words. So just again, what is this? In light of this paragraph right here, unpacking the definitions of absolute values, this limit right here means that if for every epsilon, no matter how small it is, you can find a delta. So I give you an epsilon. We're gonna play a game. I give you an epsilon. You find this delta such that whenever x is in this open interval, that is when it satisfies this inequality right here. That's what it means to be in that open interval, is to satisfy this inequality. F of x lies in this open interval. And what does that mean? It means that you satisfy this inequality right here. So another way of thinking about this is that um, if you are close to the function is functions are mappings. They send points to other points. They map a point to another point. So like we can represent this by an arrow diagram. We can represent a function geometrically by using arrow diagram, and as in this figure. And so the idea is when you're taking a limit, if I give you this interval right here, this epsilon, what that means is that you can find a delta over here, such that if you take centered at A, but possibly not containing A, and if you take it any point in this interval, it has to map into this one. In other words, like points that are what this says is that points that are close to A get mapped to points that are close to L. Their f of x is going to be, so f of x is maybe right there, it's indicating. So this point right here gets sent to this. So x is close to A means that f of x is close to L. That's what that limit means. If your limit doesn't exist, then you don't have this behavior. You could have some really odd behavior. Um, and so that's one way of thinking about it. This one's not maybe as helpful. This next picture is going to be much more helpful. So basically we have a function. It's not defined. You can see it's not defined at A, but that's okay. It doesn't matter. And we want to take the limit as x approaches A. So we want to, just to remind you, oops, it's freezing. Don't know why we're having trouble. Oh, all right. So just to remind you, what we're doing is we're computing this limit right here. The limit as x approaches A, and we're saying that it equals L. So we're assuming that this statement holds. That is, we're assuming that this awful epsilon delta definition is true. So what does that mean then? It means that if I give you an epsilon, so this epsilon right here, basically you have this number L and you have this like band around it. So you could be L, so this point right here, oops, this point right here is going to be L plus epsilon. And this point down here is going to be L minus epsilon. And then this is the line, you have this horizontal line, y is equal to L minus epsilon. And then you have this other horizontal line going this way. That is y plus epsilon. And basically what that means is if I given this epsilon right here, which gives this band around L, you can find x, or sorry, you can find delta so that when x is in this interval about here, all these points, they get mapped to inside this band right here. Meaning, like, in other words, like the graph doesn't like somehow just go off outside. The graph doesn't, instead of like going down like this, it maybe diverges up here or something like that. That can't happen if you're assuming that the limit exists. So that's what that's saying. If you can find this, if I give you this epsilon, you can find this delta. Um, so what do they say about this? Yeah, I don't think there's much more to say about this, but it's just another way of visualizing. And of course, if none of these visualizations help, that's perfectly fine. Like if you can just look at the definition and be like, okay, yeah, this sort of makes sense. That's a perfectly valid way to go about this. And if for some reason it doesn't make sense, which is probably won't, because this is your maybe your first time seeing this as a very abstract definition, that's perfectly fine also. A lot of people make the mistake that in order to do mathematics, you have to be brilliant, you have to be some sort of genius, and that's not true at all. It's just about being persistent and making sure that you are repeatedly exposing yourself to the material. So rather than spend like hours and hours and hours staring at definitions, poring over definitions, and trying to solve problems, just look at a definition, write the definition down in your own words, think about it for a couple minutes, and then move on and do something else. And then later in the day, write the definition down, think about it a little bit, contemplate it a bit. And what's going to happen is that all these ideas are going to be like stirring about in your subconscious. And so while you're brushing your teeth, while you're walking to class or whatever, while you're driving your car, while you're taking the bus, when you're sleeping at night, your subconscious is now making all these connections, and then you're just going to understand this stuff. So it's just going to take time. And being able to do mathematics is not about being brilliant at all. It's not. It's not. It's not the case at all. So this is a complicated definition. So let's try to like figure out how do you actually use the definition? How do you use the definition to prove limits? So I'm gonna pull up. I exited out of OneNote, but I wish I didn't. Um, so I'm gonna pull up OneNote, and we're gonna work through some examples. And then we'll go back to the book though. All right, so let's see. So this is not, we're not in this section. We're in 2.4, and we want to prove that the limit as x approaches 3 of 4x minus 5 is equal to 7. Actually, I will pull the book up because there's a picture in here that maybe will, why do I want to use that picture actually? No. All right, so well, you might wonder like how did you get this? How do you know that this is the case? Well, you can look at the graph, you can do some numerical calculations um to like get a guess. And this is like a guess, and now we want to prove it. Now there's going to be two stages to the proof. There's going to be first what I guess the book is calling the preliminary analysis. This is not the proof. This is just figuring out the delta you need given an epsilon. So we're going to say let epsilon be given. It's some number. We don't know what it is. And then what we want to do is we want to play this game, epsilon delta game. So we want to find delta such that the following holds. Such that if x minus 3, absolute value x minus 3 is greater than 0 but less than delta, then f of x, well, actually we're not calling it f of x. We're just saying then 4x minus 7, or sorry, 5 minus 7 is less than epsilon. So this is like our function f of x. So we're saying f of x minus, and then this is like L right here. So this is what we want to do. I'm going to give you an epsilon, and you want to find a delta such that if this statement holds, then this statement holds. All right, well, let's like fiddle around with this one and see what happens. All right, so first of all, we have 4x minus 5 minus 7. All right, so let's simplify this a little bit. So simplify this, we get 4x minus 12. And actually, from here, I can factor out 4. So we get x minus 3. Okay, that's kind of looking good because I have an x minus 3 right here. And now I can factor out the 4 to get 4 times absolute value of x minus 3. So, and what we want to do is we want to prove that this is going to be less than epsilon. We're given an epsilon, and we want to find the delta that implies that this is the case. So this suggests that we should take delta to be epsilon over 4. So this is just the guesswork. We didn't prove anything. Now, let's prove that this actually works. So here is step 2, and this is the proof. And it's almost going to look like the same sort of manipulations of steps, but it's definitely logically different. So it's going to start out the same. So given epsilon arbitrary, just any general positive number, we're going to say choose. So now we're not just guessing or suggesting that delta should be just, we're going to actually choose delta to be epsilon over 4. Now we're going to do is suppose, so what we want to prove is that if this is true, then this is true. So we're going to assume that this is true and derive this as a consequence. So we're going to suppose that absolute value of x minus 3 is less than delta, which we know is equal to epsilon over 4 because we chose it to be. Now let's prove that this right here is less than epsilon. We're going to basically do the same calculation we did. So we have absolute value of 4 minus x, sorry, 4x minus 5 minus 7. And now we're going to do the simplification like we did above. We're going to factor out the 4. And now this is the difference with the above step. With the above step, we don't know what this is less than. But if we choose this to be our delta, then we know it's going to be less than because we're assuming that right here. And so because this is going to be not equality, but less than 4 times delta. All right. Actually, let me write this on one line. This is kind of, I don't like this. So we have is that so we factor out the 4. It's 4 times x minus 3. And now this is going to be less than 4 times delta, right? Because we assume that x absolute value of x minus 3 is less than delta. But delta is equal to epsilon over 4. So it's going to be 4 times epsilon over 4. And the 4's cancel out to give you epsilon. So this proves that this, in fact, this right here is going to be less than epsilon. So this choice of delta was the right choice. You could there are actually lots of choices. You could just take, really, you don't need to take delta to be this. You can actually, let me just say that, no. You could actually take delta to be, you don't have to take it to be equal to epsilon before, but you can just take it to be any number smaller than epsilon over 4, and the exact same proof will work. All right. Let me show you one more example. Let me show you an example for the book. This one's a little more complicated, but I think it's interesting. I will definitely not give you anything this complicated. I probably won't give you any epsilon delta proof. Maybe I might give you a bonus problem or something. I'm not sure. I haven't figured it out yet. But definitely nothing as complicated as 3. But just to show you how another example of how this proof works. So we have this statement here that we want to prove. We want to say that the limit, actually, I want to know one more thing about this. So what we proved is in this problem is that this limit as x goes to 3 is 7, but notice what happens when you plug 3 into this function right here. So it'd be 4 times 3, oops, minus 5. It's gonna be 12 minus 5, and that's 7. That's exactly our limit. And this is actually going to be something that's true more generally. It's going to turn out that this is actually going to characterize continuous functions. So this function right here, this is just a line. It's whatever, again, whatever we haven't formally stated what a continuous function is, but however you define it, that lines should definitely be considered continuous. So you better, if your definition of continuous doesn't include lines, you're at the wrong definition of continuity. So this is going to turn out to be a continuous function. And it turns out for continuous functions, this characterizes them uniquely, or not uniquely, but it characterizes them that their limits. So let me I can just write it down. So f is continuous. So at say some number c, if the limit as x goes to c of f of x is equal to f of c. So in other words, to compute what this says is that like the value that you approach as x approaches c for the limit, just as the limit it's just the value of the function at that point itself. They're one and the same. So in other words, like you can't have something like this open hole and then it jumps up and then it kind of goes like that, because the limit value, which is this point right here, is going to be different from the actual value of the function. This would be not continuous according to that definition. And also just intuitively, this is not going to be continuous. So this is going to be a really important property. It's going to simplify limits tremendously. So the idea of mathematics is to start some basic ideas, some foundational ideas, like for example, the limit. This is going to be a foundational concept in calculus. And to to state these definitions and these fundamental ideas as rigorously as possible, which is what we did. We stated this as rigorously as possible. But now from there, we want to deduce properties of limits, say, or properties of continuous functions, so that we don't have to constantly appeal to that technical definition. And this is one thing that we're going to see, is that we're going to prove that a lot of different functions are continuous, and it's going to simplify limit calculations tremendously, where we don't even have to appeal to the original epsilon delta definition of a limit. So that's something we'll see in a bit. I just want to point this out for this example, but let's move on to this example right here. So here's the first part of this step. We want to guess the value of A. So I give you an epsilon, could be anything, and we need to find a delta such that if this is the case, if this inequality holds, then this inequality holds as well. So let's try to like fill around with this part of the statement. So the thing to do is to factor this like here. And then, so this statement right here is equivalent to this statement right here. So if you can show that so in other words, what we want to do is we want to find this delta such that if this is the case, this is the case. Well, if we have such a delta, we know that this part is bounded, so that this factor right here is bounded. So then the next question is like, all right, how do we bound this factor right here? Let's think about this first, this leftmost factor. We have this x minus 3 controlled by this delta right here, because we will be assuming that this is true. But let's figure out if we can like bound or control this leftmost factor. And we can actually. So just ignore this. This is just unnecessary. So what we want to do is we want to bound this quantity. And it turns out it's going to be bounded by 7. Why? Well, we're only, as it says, since we're only interested in values of x that are close to 3, we can actually just assume that x is at least within a distance of 1 from 3. So we can assume this, right? In fact, x minus 3 will probably be a lot closer to x will be a lot closer to 3 than a distance of 1, probably. But at least it will be less than 1. That's reasonable soon, because we want x to be very, very close to 3. Now, if you unpack this inequality right here, it's going to be -1 less than x minus 3 less than 1. Add 3 to both sides, you get x is greater than 2 but less than 4. And then add 3, so this implies this implies this implies this. Add 3, you get 5 is less than let me say this implies that 5 is less than x plus 3, which is less than 7. And of course, 5 is definitely greater than 7. So we have x minus 3 is greater than 7, but less than 7. So that implies that x plus 3 is less than 7. So we've bounded it. We've bounded this x plus 3 factor. So now we have, as it says, we need two restrictions on x minus 3, okay? So again, we're not in the proof stage. That's coming up right here. We're not in the proof stage. We're just in the guesswork. We're playing the epsilon delta game first. So there are two restrictions that we've imposed on x minus 3. On the one hand, we said because x is close to 3, this distance has got to be at least less than 1. But also, we need this to be the case also. We need the absolute value of x minus 3 to be less than epsilon over 7 because of this thing right here. Because we've just shown that x plus 3 is less than 7. So we can just like divide both sides basically and get that. So what we need to make sure that both of these inequalities are true, right? And the way to do that, so this is how we're going to choose our delta. We're going to take delta to be just the minimum of 1 and epsilon over 7, just whichever one's smaller. Whichever one's smaller. Now we're going to show that this is the right choice for delta. So again, we start out with assuming epsilon is arbitrary, define delta to be this, and now we're going to assume that this is the case, okay? So now if you assume this, then you know if x minus 3 is less than delta, and delta is smaller than 1, or it's smaller than 1, then we know x minus 3 has to be smaller than 1 also, because it's smaller than delta. And then you can use that to prove, which we did in the first part, that absolute value of x plus 3 is less than 7. Now we also have based on how we chose delta to be the smaller of these two numbers here, we also have that x minus 3 is less than absolute value of x minus 3 is less than epsilon over 7. So we have this holds and this holds. And using those together, we can get the conclusion we want, because we start with this, which we want to show is less than epsilon, right? That's what we want to show. We want to show that this is holds, then the absolute value of x squared minus 9 is less than epsilon. So let's show that. Well, you factor it. On the one hand, we know that this factor right here is less than 7, so that's why we get that this is less than 7. But on the other hand, we know that this factor here is less than epsilon over 7. So then in total, this thing right here is less than 7 times epsilon over 3. 7's cancel, give you epsilon. So this shows that x squared minus 9 is indeed less than epsilon. So again, this is a much more complicated example. They're not gonna, if I give you an example, it will definitely not be this complicated. But this is also motivation to get away from having to prove limits by definition. And why is that? Well, notice here's another thing to know about this example. If you plug in 3 to the function x squared, 3 squared is equal to 9, which is exactly your limit. And this is just a reflection of the fact that x squared is continuous. So if we can prove that large classes of functions are continuous, then we can avoid all this horrible work right here. I mean, this is good because it's like instructive. It helps you to learn some mathematics and possibly some techniques that you can use to solve other problems. But this could get really tedious really fast for more complicated examples. Like, for example, you could be asked to say, compute the limit as x goes to 3 of, say, 5x to the fourth plus 10x to the third plus 2x squared plus 1. And without knowing that this thing is continuous, you'd first have to guess what is this limit, and then you'd have to go through all this horrible manipulations. You'd have to play this epsilon delta game to prove that the limit equals that. But we can say that this is continuous, so the limit equals, well, you just plug in the 3. So we want to get to that point. And I'm not going to actually go through the calculation because well, maybe I can do it. No, I don't think I can. I can't do the arithmetic in my head at all. Um, but anyways, you can, I mean, this is much more manageable. Just doing a simple calculation like this than trying to go through all this work for this example. So the point is we want to move away from this eventually because these calculations could get really horrible. But if we could prove that this is continuous somehow, then we would be good. We would be done. And we can. It's not that hard actually. It's much easier than proving this function right here is continuous is much easier than evaluating this limit, but in order to do it, you need to develop some theory. And that's the whole point of mathematics is like starting with some basic ideas to describe some phenomenon in nature, formalizing all the ideas mathematically, and then deriving consequences. That's the whole end game of mathematics, basically. So we want to get to that point. So now we talked about limits, and we can talk about one-sided limits, and we can talk about a precise definition of these. So we'll just look at the left-hand limit, and the right-hand limit is not much different. Actually, the only difference is this part right here. Oops. This inequality and this inequality. So notice, if x satisfies this inequality, you can say all of these x's are to the left of a, which is exactly what we want to do when we compute a left-hand limit. When we take x to approach a from the left, we want to consider values of x that are to the left of a, and that is any x satisfying this inequality will be to the left of a. So what does this definition say? It doesn't say much it doesn't say a whole lot different than what the just regular definition of limit says. So this notation right here means that for any epsilon I give you, you can find a delta such that when this inequality holds, this one does too. So in other words, when x is really close to a from the left, then f of x is really close to L. As close as you want for any epsilon. You can find this delta right here. And the right-hand limit says basically the same thing. And you just as in the case um with limits, you can express this in terms of intervals, open sets. So you don't have to talk about inequalities and distance functions. Because remember, as I said, some spaces don't have distance. Actually, and you can't, some spaces don't have orientation to them. They're surfaces, for example, they're non-orientable. I think there's the Mobius strip, I think. Let me see. Mobius band or strip. It's a weird surface. It's a surface with one side, which is really bizarre. And I don't think this has an orientation. So some spaces that you look at, this would be an example of a topological space that is much different than um, the real line state, which is all we're dealing with. The only topological space we're dealing with is the real line. But this Mobius-Bander strip is a really bizarre space. It has, I think it's non-orientable. Let me see. I can't remember the exact. It's a two is strip it. It's a two-dimensional compact manifold with a boundary. Yeah, and it's a standard example of a surface that's not orientable. So there's no direction. There's no like you can't say that something is to the left or to the right of something. It doesn't make sense to talk about something being to the left or the right. So yeah, the Mobius strand is really interesting. Okay, I guess this guy proves it right here. This is a really helpful website, by the way, Math Stack Exchange. I use it. Obviously, I have a profile here. You can see. I ask a lot of dumb questions on this website all the time. Um, so yeah, this guy proves it. This is well beyond the scope of the course, but the point is like this is you can't always talk about left and right hand limits and left and right hand continuity and because your space might not be orientable like the Mobius span. So there's a lot of weird spaces that you'll encounter when you go further into mathematics, and I hope you do because mathematics is the queen of the sciences, as they say. It's so it's just this amazing branch of field of knowledge, and it's the foundation for all the sciences. All right, so let's look at let's see what else we have left in this. All right, so let's just go through this example. There's not much here. We're actually going to prove a law, which is going to be really useful. This is going to be the first step to proving there's this limit law right here. Um, this is going to be the first step to proving that polynomials, for example, are continuous. So let's look at this example first. So we have definition. So we want to use definition. So we want to compute this right hand limit of the square root function. And we want to prove that it's zero. So we want to use definition 4, this one right here. So again, there's two stages. There's like the guesswork. You play the epsilon delta game, and then once you've played the epsilon delta game, you found the delta that you need, then you can actually show that that delta works. So you take a to be or epsilon to be positive. The a is a 0 in this case, L is 0, and so what we want to find is a number delta. You're probably reading it. I'm giving it away already, but whatever. So what we want to do is we want to find delta such that if x is less than delta, then the square root of x, absolute value of it, is less than epsilon. But of course, this line simplifies to this. If you square both sides, you get of this right here, you get this. So this pretty clearly suggests that you should just take delta to be square root of x. So this one is a pretty simple proof. And or this isn't the proof part, but this is a pretty simple problem. Now let's go through the proof. So you take epsilon to be arbitrary, take delta to be epsilon squared. This is the epsilon that we got from playing the epsilon delta game. And now you're going to assume that x is between 0 and epsilon delta. So that means if this is the case, then you can take the square root of both sides, right? And so if x is less than delta, then the square root of x is less than the square root of delta. But delta is just epsilon squared. So you're taking the square root of epsilon squared, which gives you epsilon. And then so you have delta x, sorry, you have square root of x is less than epsilon. And that's the same thing as square root of x minus 0. Absolute value is less than epsilon, which is exactly what we want to prove. All right, so let's look at this. Um, oh, actually, you know what? I'm gonna stop here. So this is referring back to a limit law in section 2.3. So this, I will jump, I'm kind of jumping back between 2.43 and 2.4. So this is all we're gonna do for this video. I will go over this limit law in the next video. This is when we're gonna start like deriving consequences and proving some things using the definition, some like general theory to help us simplify calculations. All right, that's all for now.